Great pleasure to welcome our first speaker for this session, Thompson from Liverpool, and he's going to speak about diffraction in Mindlin plates.
Right, thank you, Sasha. So just before I start, I'd just like to yeah. Yes, you have to really force people to come to my talk. I'll go and drag them in. So yes, I'd just like to remind everyone of Anastasia's suggestion of putting together maybe a booklet of unsolved Wiener-Hopf problems, which I think is a really nice idea. This is one I'd like to throw out. If you take the classic Hills and Karp paper, where they look at scattering by a semi-infinite row of objects, and make the objects a bit bigger, so that in their problem they're small compared to the wavelength. If you make them a bit bigger, you'll get a very, very nasty matrix Wiener-Hopf problem immediately. And I've known about this for years, and I had no idea how to solve it. I think that the probability of an explicit solution is somewhere between 0 and epsilon, but I did wonder whether the method that Elena Luca was discussing might lead to something. So that will be my suggestion, and there will be a bit more detail in the booklet. But if anyone else has problems that they'd like to throw out, please do send a brief sketch of it to one of the organisers, and we'll put something together. Depends how big your scatterers are. So the first problem up from Hills and Karp would be a 3x3 problem, because essentially, I shouldn't talk too long about this because this isn't my presentation, but essentially Hills and Karp have a field that looks like that, where you've just got H0. If you have larger scatterers, you have a sum over n, and the bigger they are, the more terms you need. So -1 to 1 is the next step up, then -2 to 2. So there is some partial decoupling, so you can probably get down to a 2x2 matrix and a scalar problem. Anyway, let's get to my actual presentation. So yeah, I'd like to discuss today diffraction in plates modelled by Mindlin theory. I did hope to be further along with this work than I actually am, but I'm always behind with things. So I don't have any results, but hopefully I can still say something of value. So I'll just say first of all that waves in plates are important because, in particular, there's an application where if you want to detect things like cracks and defects in thin structures, panels and things that you might use in aeroplane wings, what you want to do is send a wave in, look at the pattern that comes back, and then you can determine whether there's any kind of defects there. Often the defects might be too small to detect by just looking at things. And a great thing about plate theory, because I know there are some plate experts in the audience, but there might also be some people who've never vibrated a plate in anger. A great thing about plate problems is, if you just think about any sort of classical Wiener-Hopf type problem in whatever sort of physical domain you're happiest with, so that might be acoustics or electromagnetism. So normally you might think of something like Sommerfeld as being a cross-section through a 3D problem. So you've got some 3D acoustic problem, and you assume there's no variation perpendicular to the board, and you get Sommerfeld. Well, just take any one of those, and just say, okay, this doesn't represent a cross-section of a 3D problem anymore. It represents a plate. And so there you have immediately a number of Wiener-Hopf type problems that you can look at in plate theory. I will discuss two plate theories very briefly. Kirchhoff, or classical plate theory, has been mentioned in I think at least 2 talks so far, Sasha Movchan's and Malte Peters. Kirchhoff theory, sometimes called classical, sometimes called Kirchhoff love, it dates back to the 19th century, and it only models vibrations perpendicular to the plate. And one way to think about it is that there are 2 Helmholtz equations, one of which gives you propagating mode, so that's this one, and the other one with this minus here, so a modified Helmholtz equation, gives you evanescent modes. You can also think about it, as Sasha did, as having, if you take the product of these 2 things, it's a 4th order PDE, but for the purposes of this talk it's slightly easier to think about it as being 2 separate ones, and then your actual physical field is a sum of those 2. And one of the interesting things about this is that you can have all sorts of singularities in these individually, and again that happened in Sasha's talk where if you look at the Green's function for a Kirchhoff plate, actually both of those are singular, but when you add them together the singularity goes away, and that can cause all sorts of fun and games with Wiener-Hopf type solutions. Everything in the talk is time harmonic, so if you want the actual physical field you just do the usual, multiply by e to the minus I omega t and take the real part. And the formula for the wave number, again, that's been mentioned already, rho h omega squared over d to the power 1/4, the density, thickness, frequency and plate stiffness there. And because you've got two terms, or two Helmholtz equations effectively, you need two boundary conditions at any interface. I did say in my abstract that I would talk about cracks and rigid edges. I'm going to talk almost entirely about rigid edges because that's the easier problem and I haven't even finished that yet. So a rigid edge, your boundary conditions for Kirchhoff theory are, well, displacement is 0, obviously, because it's a rigid edge. Not quite so obvious why the normal derivative of displacement should be 0, but I'll come back to that in a moment. And there's a further condition for Wiener-Hopf problems, which is that the strain energy density, and I won't give the formula for that, it's quite long, but strain energy density must be integrable in all regions of the plate. That's what you need if you're doing something like one of these problems and you'll need some sort of tip condition when you get your entire function in your Wiener-Hopf equation and you want to show that the entire function is 0, you will need this condition on strain energy density. What about Mindlin theory? So Mindlin theory is much newer. It was developed by Raymond Mindlin in the 1950s, and the extra ingredient that it has is it does include some in-plane motion in addition to the out-of-plane displacement. And in terms of maths, the extra ingredient is now there's a third Helmholtz equation. Okay, so you've got these two that you had before, and this one that you didn't. So K1 is real here, so that's going to give you your propagating terms. K2 is imaginary, and K3 is also imaginary, usually a lot bigger than K2. So these phi terms, they're very strongly evanescent. They really only matter very close to a boundary, and then they decay away very, very rapidly as you move away. And as I said, you've still got the transverse displacement, and that's still just the sum of W1 and W2, but you've also got these in-plane rotations, and they're given by these formulas, so they're just partial derivatives of W's and phi, and these A1 and A2 are just constants. Because you've got 3 Helmholtz equations now, you need 3 boundary conditions at an interface. And actually at a rigid edge it's really easy. It's a rigid edge, there's no displacement, so all 3 of your displacements have to be 0. And also, rather conveniently, if you, again, I haven't given the formula for strain energy density because it is rather long and it would take up half a slide, but if you take that formula and just say, well, actually I'm going to insist that all my displacements are bounded, which is a fairly reasonable thing to do, then in fact you find that strain energy density is automatically integrable. So in fact the tip condition for Mindlin problems is simpler than for Kirchhoff problems. You don't need to look at strain energy density, you just have to say, I want everything to be bounded, all my displacements, and you will get a unique solution. What's the relationship between the two? Well, if you let omega tend to 0, it's relatively easy to show that K1 and K2, these two wave numbers for Mindlin theory, K1 tends to K, the Kirchhoff wave number, and K2 tends to IK. So straight away you recover the 2 Helmholtz equations for Kirchhoff theory. But what happens at the boundary is a bit more subtle than that. It's quite easy with rigid edges though. So if you look at these 2 constants A1 and A2, they both tend to -1 as omega tends to 0, so that's their leading order behaviour. So if you now take the formulas for the in-plane rotation vectors and let omega tend to 0, what you will get, instead of a linear combination of W1, W2 with different constants, at leading order they're the same, they're both -1. So in fact you get your physical displacement, W, so you get minus dW by dx here and minus dW by dy. But of course at a rigid edge you know that W is 0 all along the edge. Well, if that's true, then dW by dx must be 0 as well. So that knocks out this term here automatically. And then you can just say, well, how can I satisfy the remaining boundary conditions? So I've got to have W is 0, clearly, it's a fixed edge, that's one condition. How can I satisfy these two? Well, it's quite easy, just take dw by dy is 0 and phi to be 0 everywhere. And that just knocks you down from 3 conditions to 2. You can just, in the case of a rigid edge, you can just, at the leading order at least, you can just throw away phi, and your 2 conditions are now w and dw by dy is 0. So that's one way of seeing why, for a Kirchhoff plate, you should have dw by dn 0 at a rigid edge. It just comes from the leading order behaviour from Mindlin theory. And there is a similar reduction. If you have a free edge, it's quite a bit more complicated, but a similar sort of thing happens, that you can reduce the 3 boundary conditions down to 2 at the leading order at low frequency. I'll go through this fairly quickly because I think everyone here knows all this stuff pretty well. If you want to take look at sort of Fourier representations, just take an ordinary Helmholtz equation, take the Fourier transform, solve the resulting ODE, and you get your usual square root type function. Conventional to take gamma of naught is minus ik, of course, and different forms for the unknown functions b and c in different regions. And for a Sommerfeld type geometry, so a plane with a semi-infinite boundary, you would normally have c is 0 for y greater than 0 and b is 0 for y less than 0 to satisfy the radiation condition. So if you then write down the inverse transform, what does it look like? It's going to be something like e to the minus gamma mod y. That makes sure you've got no waves incoming from infinity, e to the minus I for x, and some unknown function b, and branch points plus and minus k, and inversion contour going over and then under. So the usual sort of thing. What happens if you take a Kirchhoff plate? Well, you can see it quite easily in your head that when you Fourier transform this modified Helmholtz equation, instead of this square root function, you're going to get this one with alpha squared plus k squared, and that's going to give you 2 more branch points. Luckily, they don't cause too much trouble because they're far away from the real line. And then when you write down your inverse transform, you've now got 2 unknown functions. What about Mindlin? Oh, and I should say, yes, lambda will give you evanescent modes, and again, you can see that quite easily because if you're on the real line, or if you're near to the real line, that's going to have a positive real part, and so that's going to just give you a load of evanescent terms. They are important near the boundary, but not elsewhere. If you now go up to Mindlin theory, you get 2 more branch points further up the imaginary axis and further down. That's for the phi modes, these very evanescent terms. So you usually, rather than inventing 3 letters, rather than having gamma, lambda, and something else, for Mindlin theory, you usually just call them gamma j. So gamma j is alpha squared minus kj squared, and you just have to remember that k2 and k3 are imaginary. So in fact, gamma 2 is a function more like one of those lambdas. And then again, you can write w and phi as inverse Fourier transforms. You've now got 3 pairs of branch points and 3 functions to find. So what's been done so far in this type of problem? Well, the main paper I'll mention is this one by Andy Norris and Wang. I don't know Wang's first name. And they looked at essentially Sommerfeld geometries in Kirchhoff plates. So incoming wave and a rigid strip or crack on a half line. 2 boundary conditions, so you get 2 Wiener-Hopf equations. Is it a matrix problem? No, it isn't. And it's easy to see that straight away. Just follow what Norris and Wang did. They split the incident wave into odd and even parts. So if you take an incident wave, which is a plane wave, and then say, okay, well, I'm going to take, this is my symmetric term, this is even about y is 0, this is my anti-symmetric term. Clearly, if I add those together, I just go back to this because I get cos plus I sine. But automatically, for the symmetric wave, you have the normal derivative is 0. And automatically, for the anti-symmetric wave, you have W itself is 0. So if you then consider those problems separately, which is what Norris and Wang do, you get 4 Sommerfeld type problems, but you only have to solve them in the region y greater than or equal to 0. Each one only has 1 Wiener-Hopf equation, and so they're scalar problems. If you do the equivalent Mindlin problems, okay, so now we're starting with 3 boundary conditions and therefore 3 Wiener-Hopf equations, you can still do a partial decoupling, but you can't get further, or at least I can't get further, than 2 scalar problems and 2 2x2 matrix problem. So each problem, one for the rigid strip and one for the crack, starts out as 3 Wiener-Hopf equations. A decoupling along these lines will break off one row of your matrix, if you like, as a scalar problem, but it will leave behind a rather difficult 2x2 problem. Now, I don't want to go through the actual derivation of any Wiener-Hopf kernels. I just want to actually talk about the kernels now. So what sort of thing do you get? These are the kernels for the rigid strip from Norris and Wang's paper. The symmetric kernel is a difference of these two square root functions, and the anti-symmetric kernel is a sum. But if you just multiply the two together, you actually find you just get a constant. So in fact, if you can factorize the symmetric kernel, then you can automatically factorize the anti-symmetric one. So there's only one to do for each of the crack and rigid strip problems. Once you've done one, you've done them both. What about Mindlin theory? Okay, well, the scalar bit that you get for the rigid strip, that's not too bad, and you can see it's got the same kind of structure. It's got a difference of these square roots. Okay, it's got this extra one, gamma 3, coming in there, and it's got this additional polynomial term. The rather frightening one, though, is the matrix bit. Okay, so that's my matrix T, and that's got these 1 over gammas and then these rather mean-looking expressions in the bottom row. If you take the determinant of T, then you get a fairly simple function times the scalar kernel, and that happens for both the crack and the rigid strip. It's related to the fact that if you do get something like an edge mode, obviously you don't in a rigid strip problem, but in a crack problem you do, then it has a component that comes from both the scalar bit and the matrix bit. So essentially, where the kernel function for the scalar problem is 0, the determinant of the kernel for the matrix problem is 0. So, what do we do with these? Well, let's just have a look at what Norris and Wang did, see if it gives us any insight. So this is Norris and Wang's Kirchhoff Wiener-Hopf equation. Kernel function k, which is the difference of square roots, unknown for plus function equals unknown plus equals known plus function and unknown minus function. So very, very standard scalar Wiener-Hopf equation. Observations: if you take the limit as alpha tends to infinity, the leading order of these two things will cancel, and you'll be left with a sort of 1 over alpha behavior. Also, crucially, if you were to wind once around both k and ik, k will change sign. Okay? If you just go around one of them, the change to k is quite subtle in that it changes the sign of one bit of it, but not the other. But if you change the sign of this and this, then clearly it just swaps them over, and you get a change of sign. And we'll see in a moment how Norris and Wang took advantage of that. But you can then write down a function k tilde, okay, I'm just multiplying by k to the minus 2 to make it 10 to 1. And I'm also going to multiply it by gamma, okay, so that's to get rid of the 1 over alpha type behavior. So now this thing tends to 1 as alpha tends to infinity, and crucially has no branch point at infinity. That was really what clever thing that Norris and Wang did, is that they write this function as one that has no branch point at infinity, because now if you go round k and ik, those change sign and swap over, gamma changes sign, overall there's no change. Gamma itself is easy to factorize. I mean, you just literally factorize the polynomial there and share out the two branch points. So they write it as something which tends to 1 times something which is easy to factorize, but also, as I say, has no branch point at infinity. Again, I can go through this very quickly. This is a standard factorisation formula for a scalar function. You can see there that if you, for the plus function, you want to integrate along this bottom contour, and for the minus function along the top one, if you add the two of them together, what you'll be left with is an anti-symmetric circle around alpha. So you can easily see that j plus plus j minus is log f, and the exponential is then f itself. The problem with this, at least for these problems, it's not always an issue, but it is here, is that the convergence is rather slow. Okay, if you're going to do these integrals numerically, you're relying on the fact that f tends to 1 to make this integral converge. It's not very fast convergence in this case. So what did Norris and Wang do? They took advantage of the fact there's no branch point at infinity. So here's a situation. First of all, an observation. Dave Abrahams mentioned this in one of his talks, that I'm only going to calculate k minus in this grey region down here. If I wanted it in this region up here, what I would do is calculate k plus and then use the fact that it's a ratio k over k plus. And that means I only ever have to calculate it well away from the singularities. Then I can do whatever I want in the upper half plane now. It's not going to change the values down here. We rotate the branch cut so that k is now joined to ik. And what that will do, at least for k tilde, which remember has no branch point at infinity, it cancels the infinite branch cut. It disappears. All I'm left with is that. And then just push the contour upwards and it wraps around the branch cut. And what you're left with is then an integral around a finite cut, which is trivial to do numerically. So the problem of convergence has gone. Well, that's all well and good, and you can do the same for the scalar problem, for the Mindlin problem, no trouble at all. Exactly the same trick. Slightly more complicated because you've got a sort of an extra branch point up here, but it's not difficult. But the question I then run into is, what do you do with the matrix? And I thought about this for a while, and I looked at various very complicated papers on matrix kernels, and I thought, well, could there be something easy you could do? Is there a way you can take advantage of having finite branch cuts? And the obvious answer is, well, no, because at the very start of a scalar factorisation, you need this Cauchy integral formula. We don't have that for matrix problems. There's no formula to start with. So, well, okay, let's just imagine we didn't have that. Let's suppose we have a Wiener-Hopf equation. Again, I'll show this for a scalar case. Let's imagine we have a Wiener-Hopf equation. A, B, and C are known. F plus and G minus, as usual, plus and minus functions. But with this extra ingredient, they only have finite branch cuts. Is there something we could do? Well, a natural thing to try is to represent these as Cauchy integrals around their branch cuts. So I write down Cauchy's integral formula. Obviously, I have to have this diversion around the branch cut to make it work. And then if G minus tends to 0 as Z or alpha tends to infinity, then I can push the contour out to infinity, and I'm just left with a bit around the branch cut. And I can do the same for F. Well, that's all well and good, but I still have no idea what these things are. But again, thinking back to the scalar problem, if I calculate these sorts of functions, I have to do it by quadrature. Okay, I can't do those Cauchy integrals exactly. So in reality, I'm only ever using a set of values at a finite number of points. So, okay, let's suppose that these Cauchy integrals were in fact evaluated by quadrature. Okay, and this I think is rather similar to some of the talks we saw last week, this sort of idea. So I don't think this is a new idea. I think it's just rather convenient when you have finite branch cuts. So, okay, suppose they're evaluated by quadrature. What would the formulas look like? Well, it would look like a sum of weights times the functions evaluated, so the integrand evaluated at the nodes. And here I've got left and right values because I've got to integrate along one side and then along the other. So I get the left value of G minus the right value, and the same for F. And yeah, that's what these big F and big G are, just the functions evaluated at the nodes. Go back to the Wiener-Hopf equation and now just evaluate it at one of the nodes. So evaluate it at one of the quadrature nodes at that point. Okay, so you get S here could be either left or right because I can evaluate the Wiener-Hopf equation on either side. So I get AS, F plus, BS. But when I evaluate G at one of these nodes, I've got a formula for that. It's just big G. It's one of these constant coefficients. So that term simplifies. And at this point, this is exact, okay? I've not introduced an approximation yet. But if I now put my quadrature formula for F into there, what happens is I get an equation, an algebraic equation involving my unknown coefficients, F on the left and right and G on the left and right. Now, how many unknown coefficients do I have? Well, assuming there's some sort of symmetry, so I use n nodes both in the upper and lower half plane, I've got 4n, haven't I? Because I've got 2n lots on here, the left and right ones, and 2n lots on there, so a total of 4n. But I can do this at any of the nodes on the upper branch cut, so that gives me n equations. But I can also do it at the left and at the right, so I can change my s here to either L or R. So that's 2n equations, and then I just repeat for z minus, and I get 4n linear algebraic equations for the 4 unknowns. So it's a numerical scheme which will factorize, or which will give me the unknown functions, at least approximately. If we just go back and compare it, what does the standard method need you to do? Okay, if you're factorising something and it's non-trivial, you're going to have to do a quadrature, and it'll be one quadrature per alpha value to split the kernel. What about this implicit quadrature scheme? Well, to do that, you need to solve one linear system for each set of physical parameters. So if you leave things like k and d and all those things the same, that won't change. And then you'll still need to do a quadrature per alpha value. So there is a cost to doing this, but there's also a benefit. Because I haven't used the splitting formula, this will work for matrix equations as well, as long as you've only got finite branch cuts. As soon as you've got infinite branch cuts, you run into all sorts of horrible convergence problems, and you'd have to do something much cleverer, I think. So I think I'm just about on time, so I'll just conclude here. I've almost finished the rigid strip problem. My numerical code isn't finished yet, and then when I've done that, obviously I'd like to actually analyse the diffraction pattern. Then I'd like to look at the crack problem, which is harder, but I think the same method will work. A couple of things I'm not sure about. Do all plate diffraction problems of this type lead to kernels with finite branch cuts? I don't know. If you take two parallel cracks, for example, will that give you finite cuts? I don't know. And if it's true that they all do, why? What is it about plate problems that gives you this property that you get finite branch cuts? Not sure about that. If you go and look at what's been done already, apart from Norris and Wang's paper, there's a couple that Dave and I wrote on anisotropic papers, and there's also some papers on discrete problems, which were again mentioned in Sasha Movchan's talk. So things where you, like the Hills and Cart problem, where you have a line of scatterers or two lines of scatterers. Some work on those, I'll give some references in a minute, but there's an awful lot of geometries that are completely untouched in plate theory. So like I said at the start, take your favourite Wiener-Hopf geometry, turn it into a plate problem, and there's a new plate, or well, actually several new Wiener-Hopf problems, because these could be rigid strips, they could be cracks, you could be working with Kirchhoff theory or Mindlin theory. So there's lots of scope to do new Wiener-Hopf problems in plate theory. So I'll just say now, I'm not a minute over because I started a bit late. Thanks for your attention, and I'll just very quickly run through these references. So if you're interested in Kirchhoff theory, standard places to look, Timoshenko's book and graphs. If you're interested in Mindlin theory, I particularly like Mindlin's original paper, but there is also some material tucked away toward the end of Graph's book. The existing papers on crack diffraction in plates, Norris and Wang, and my own paper with Dave Abrahams, where we looked at fibre reinforced plates, and then these problems on these discrete Wiener-Hopf problems, Evans and Porter, and Haslinger and Friends, 07 and 2016. And like I said, aside from those, there really isn't that much that's been done. So there's lots of possibilities for more Wiener-Hopf analysis in plates. Right, that's me done, I think.
I don't think Evans and Porter did Wiener-Hopf problem. They had finite clusters and also infinite grating and scattering. I don't think they had Wiener-Hopf.
I'm fairly sure they did do maybe not in that. Maybe I've got the wrong, because they wrote two papers, didn't they?
Not on this one.
Not in that. Yeah, I think maybe I've put down the wrong. I was doing my references slide at 11 o'clock last night, and I think maybe I've put down the wrong paper there.
No, but title is right. Diffraction in plate, so it's okay.
Right. Yeah. Okay. But I'm fairly sure there is an Evans and Porter paper with a Wiener-Hopf analysis in a thin plate with pins in it, and possibly I've given the reference to the wrong one there. So I apologise for that if that's a mistake.
Okay. Questions, please.
A naive question. So, if, as you explained, there is a Kirchhoff theory, Mindlin theory. One is the limit of the other, right? In some sense, when this small parameter,
yes,
additional degree of freedom tends to 0. Then we translate both to Wiener-Hopf language, leap and difficulty from, scalar to matrix, right? Decoupled. So, would it make sense to do something in between, like slightly Mindlin theory, Kirchhoff with a small parameter symptotic perturbation, and to understand how this...
It may. I mean, this is something that I intend to look at when I have the solution, is how do the two relate to each other. it's not that obvious how the sort of, when you have this Mindlin type branch cut structure, which is miles back, isn't it? Yeah, it's not that obvious how those branch points at plus and minus K3 sort of lose their influence as omega goes to 0.
They go to infinity, right?
Go to infinity.
Yeah.
They disappear.
Right, they go to infinity, but then doesn't that leave you?
Well, they have gone to infinity, right? You have like a matrix which is
Yeah.
right? Asymptotically in some sense.
Yes, yeah.
How does
Yeah.
it appear in the formulation?
Hmm?
How that would appear later on is quite interesting.
Yeah, it's certainly it's something that I need to look at, but as I say, it's not. I'm not quite that far on yet. I'm still battling to get this matrix kernel to behave itself. Yep. Oh.
So I think this approximation method is very much linked to approximating by polynomials, right? Because you're picking a few points at which you are.
Yes.
It's basically approximating this function by a polynomial, and then you're finding those constants.
Yes. Yeah, I suppose if you're using quadrature in effect, then you're always approximating by polynomials of some sort.
So, I mean, my comment is that if you use rational functions, you have fewer constants to find with the same.
Yeah, again, it's something that would be interesting to look at. That you know, given that this scheme is quite simple, how does it compare to cleverer schemes like yours? It would be interesting to try that, and it is something I would like to do. But yes, when when I get round to it.
If you use quadrature smartly, then it's tantamount to doing the same thing as using Chebyshev points or some other points, and so whichever scheme, it'll all work, won't it? If you have a finite cut in the limit, some may be slower than others.
Yes, I mean you can, because these K3 branch points can move quite a long way. You do often need quite a large linear system, but then of course, on a modern computer, what's the price of solving a large linear system? It's 0, so who cares? So yeah, but it would be interesting to see, how, in terms of accuracy, how this thing compares to cleverer approaches.
Yeah, of course, in the Timoshenko theory, there's a shear correction factor about which much has been written to the exact value. Now, do you take a particular value? I don't think, unless I missed it, you didn't discuss, did you, a particular value?
No, I didn't. Yes, there is this parameter, which I can't remember what, there's some range that it's allowed to live in, and yes, there's a debate about what value. In the tests I've done numerically, I've just lifted a value out of one of Andy Norris's papers.
Does it make much difference within that range? But
No,
but you've chosen pi squared over 12. Or
something like pi squared over 12. Yeah, I don't have any great insight into what the right value for that is.
Pi squared over 12, but in one paper it's meant to be the ratio of the two speeds of it sounds like the Rayleigh wave speed versus.
Yes,
yeah,
I think.
that's a matching up in.
Yeah, I think Graph sort of discusses the different choices and what they do, and I think Mindlin just sort of says it's got to be between these two values. So I haven't any insight into that. I've just nicked a value out of someone else's paper.
Okay. Can I suggest that we thank Ian for a very nice lecture?